Hi everyone, my name is Chen, and I'm a third-year PhD student from Georgia Tech at the Localized Science and Technology Lab. Today, I'm thrilled to talk about my work on investigating the expulsion dynamics of saturated cold gas propellant in microgravity. This is the continuation of my previous work on developing a thermal-capillary propellant management device and system for distributed CubeSat architectures. So let's get right into it. With the global space economy projected to reach almost $2 trillion by the year of 2035, small satellites are at the forefront of this development. Its growth is being driven by numerous stakeholders, including telecommunication providers, Earth observation services, research institutions, and commercial defense contractors, and more. As more and more small satellites are being deployed into orbit, operators are increasingly relying on distributed architectures to achieve both scalable and robust mission designs, such as in the way of swarm and formation flying. However, these architectures require self-maneuvering satellites capable of extended operations. As a result, propulsion systems that are simple, offer high impulse per stall volume, precise impulse delivery, and are reliable are highly desired to maximize return on investment. In particular, cold gas propulsion systems that rely on self-pressurizing propellants such as R236FA are highly utilized. However, managing these saturated propellants in microgravity is no easy task, owing to challenges such as the presence of a conformal tank geometries and two-phase storage. Couple that with the fact that current propellant management strategies, such as the implementation of the two-tank planet systems, are volumetrically inefficient, with upwards of 30% of tank volumes being unusable for propellant storage. As a result, there is a clear need for a more compact and power-efficient CubeSat propellant management strategy. So, to address this challenge, we propose a novel propellant management strategy through the use of thermal-capillary propellant management device, also known as a PMD. Our experiment, VAporization for propellant repositioning vapor, operates upon the principle of thermally induced phase change. Essentially, by vaporizing propellants near a heat source, it causes it pressurize within the tank that drives condensation of vapor bubbles in the colder regions. By carefully placing this heat source next to an outlet, one can easily extract the outlet's volume to generate thrust for satellite maneuvers. With our ultimate goal being impulse delivery, one must first generate some bubbles before we can deliver that thrust. As a result, let's take a quick overlook of the vapor experiment and see how we got ourselves here. Our original experiment, Vapor, sets out to test a collection of PMDs' ability to both reposition and retain propellant ullage in microgravity, with the microgravity conditions being provided by a series of parabolic flights. The PMD themselves feature various heater configurations and capillary structures for ullage retention. Beyond Vapor, there was also the Vapor Drift experiment, which is a free-floating experimental platform developed to provide high-quality microgravity conditions to residual acceleration-sensitive experiments, such as the proposed sponge star basket on the bottom right of the screen, as well as the magnetic positive positioning experiment. In general, our design enables ullage repositioning without the use of moving parts and accommodates a wide range of tank geometries, offering a compact and reliable approach to propellant management. As shown in this side-by-side comparison, all of the PMDs are successful in repositioning propellant, with the patch heater on the left generating the largest bubble at the fastest rate. All of the capillary structures are successful in retaining the generated ullage, and these results highlight the importance of thermal inertia in system performance, with additional lessons learned such as material compatibility. Great! With Vapor, we've generated our starting ullage, and now it's time to say goodbye to them in order to achieve impulse delivery. The goal of the Vapor Vents experiment is to decipher the uncertainty in how ullage dynamics and thermodynamic environments evolve during propellant expulsion in microgravity, particularly investigate the interface evolution, thermodynamic response, recovery time, and stability upon propellant expulsion. We aim to identify and mitigate the reliability risks associated with the Vapor technology. Here's an overview of the Vapor Vents experiment. It is housed in the same 80-20 frame that houses the Vapor VMDs. It features two propellant tanks, with one being the unvented control case and the other being the actively vented tank that is connected to a complex pipe connection systems that allows us to extract ullage and quantify the changes downstream. The venting line itself is comprised of 1/8 inch inner diameter 316 stainless steel tubing, which routes from the outlet of the propellant tank to the aircraft venting port. A pressure transducer and thermocouple are mounted within the manifolds to record downstream pressure and temperature changes. Additionally, a needle valve is installed within the system to enable manual adjustment of the flow rate, and a ball valve is used for emergency shutoff. In regards to the thermal PMD used in the vapor experiment, a stripped-down version of the cartridge heaters was used. It protrudes approximately 1.5 inch into the fluid, with wire leads soldered into its terminal along the perforated cage, and it does not feature any capillary structures. The activation of venting is dictated by a solenoid valve that is connected to the dispensing needle within the propellant tank and is actuated manually by operators during the flight. The propellant tank also features a plethora of transducers, including both 4 thermocouples and pressure transducers. Our results have indicated that as venting proceeds, the vapor volume within rapidly contracts. During this process, continued vaporization is observed both within the PMD and along the external heater wires. Following a valve closure, accelerated bubble growth is observed along heater segments located outside the PMD, suggesting that these elements are acting as thermal hotspots that promote unintended vaporization outside of controlled volume, reducing ullage extraction efficiencies and reinforcing the need for better thermal confinement. The following are some of the major takeaways at an interfacial perspective. As indicated in the time-lapse, the PMDs generate ullage at a much faster rate compared to previous cartridge heater tanks featured in the vapor experiment. The PMD refills within 3 seconds and is vented away within 0.5 seconds. Our time-lapse has also shown unintended vaporization at the protruding heater elements, which, upon venting, boils at an accelerated rate and increasing the unusable ullage loss. Now, let's turn our attention to the thermodynamic response of our system, both within the propellant tank and downstream in the venting line. Beginning with the overall thermodynamics evolution within the propellant tanks, we observed that the venting tank is maintaining a consistently lower pressure than the control system, with a final pressure of 37.5 versus 40.4 psia, despite starting at a slightly higher pressure. This observed effect is the consequence of the venting procedure. As venting proceeds, the tank pressure drops beneath the saturation pressure, leading to additional vaporization to restore the phase equilibrium. This process absorbs latent heat from the bulk fluid and thereby cooling the system and reducing the baseline saturation pressure. In regards to the system's temperature, we can see that venting of the propellant tank has dramatically reduced the temperature spikes at thermocouple location 1, which is the one directly adjacent to the heater. This observed effect is the consequence of the latent heat absorption due to vaporization, as well as the lack of sustained flame boiling within the PMDs owing to the now vacated PMD ullage from the system. Now we focus on the thermodynamic response both in the tank, as shown in the top graph, and downstream in the venting line, as shown in the bottom graph, during single firing events, in which the venting only proceeds once during the 20 seconds of microgravity duration. We can see that in upstream, the tank pressure drops by approximately 2 psi, indicating the extraction of ullage from the system. Meanwhile, downstream in the venting line, the temperature plummets and reaches the lowest detectable temperature limit of the probe. This observed cooling curve in the second plot is estimated to be the consequence of cooling by vaporization of the residual liquid adhered to the thermocouple and the thermal response time of the probe itself. The pressure in the venting line experiences a sharp spike during the venting event and is followed by a sharp decay rapidly owing to the depletion of gas ullage. The duration of the spike roughly matches the 0.5 seconds of predominantly gas ullage venting observed in the videos. Across the different microgravity durations, this spike ranges anything from 4.3 to about 8 psi and appears to be independent of the in-tank initial pressure. In multi-firing events, The thermodynamic response appears to be similar to that of single firing events, where we observe similar pressure drop in tank and temperature drops in venting line. In addition, repeated venting within the short microgravity duration has shown a significantly decreased downstream pressure spikes, with the second and third venting event leading to pressure spikes only 20 to 30% of that of the first spike. This indicates the system warrants a longer recovery time in order to achieve impulse delivery of same magnitude. So now, on to the part where engineers truly care about, impulse delivery parameters. We would like to first acknowledge that we're building a propellant repositioning system in this experiment, which is a subset of the propulsion system of a spacecraft. The goal with the Vapor experiments isn't to build a full-fledged space propulsion system, but rather explore the viability of implementing the Vapor technologies into a proto-system. With that in mind, the Vapor vent system has achieved an average mass flow rate of roughly 0.8 grams, fed at a mean tank pressure of 35 psia, which, during venting, varies anything from 38 to 33 psia. If we were to operate at orbital operational parameter with a mass flow rate of 0.057 grams per second, for example, which is used in previous small-sat missions such as the BioSentinel mission, a fully filled PMD can allow for 7 seconds of sustained venting. If we were to assume a heater power of efficiency of 75%, 11 watts of power input can enable continuous venting of the system. Moving on to thrust and specific impulse evaluation, our first order estimation used a peak thrust of 0.19 newtons at an ISP of 24 seconds in testing conditions, which was being vented into an airplane venting port, which is at 12 psia. In vacuum, this performance will improve and translate to 0.32 newtons of peak thrust and a specific impulse of 41 seconds. Lastly, it is worth noting that at the maximum allowable storage pressure, which is typically at 100 psi for ride-along payloads, the warm-hot gas capabilities of Vapor has the potential to more than double the ISP of the system. To sum up our discoveries, thermal capillary PMDs are effective in repositioning and retaining two-phase saturated propellant. Our refined PMD has shown its capability in refilling the PMD internal volume with gas within 3 seconds, which would then sustain up to 7 seconds of continuous thrusting under orbital operation conditions. Vapor is promising in a way that it supports both continuous ullage generation and offers warm/hot gas venting capabilities. Our upcoming work includes optimizing the thermal performance of the PMDs, thermal vacuum testing of our impulse delivery systems, followed by a comprehensive system demonstration in a standard duration microgravity environment, where the propellant repositioning and impulse delivery system sequence is going to be validated. Additional work includes controller design to enable repeatable impulse delivery and ullage sensing capabilities. Overall, the Vapor technologies support the advancement of distributed CubeSat architectures, including formation flying and swarm architectures, addressing a critical gap in this rapidly growing multi-billion-dollar smallsat market. Here's a list of publications relevant to what we've discussed. We welcome you to read any one of them. Thank you for your time once again, and I'm happy to take any questions you might have.